Thank you, Cassidy. As she mentioned, please feel free to interact with us via that community post. If our explanation is not understandable or if there is a still gray area, do not hesitate to repeat your question. Uh, Before joining Wolfram Research, I spent more than 15 years of my life just being in academia, being an educator. So the least that I learn is when it comes to learning, you really need to be patient and being ready to repeat and repeat and repeat and repeat. So don't be shy asking the same question over and over again. We don't mind explaining that. At least I don't mind. Maybe maybe Nick would say, learn it yourself, but it's
No, no,
I'm
no. Yeah,
patient.
I agree with you. I agree.
Yeah,
Keep
I'm
it
teasing
simple.
you, because Nick, growing up with a different, education system, both of us completely different. So uh, that interaction is interesting. So, what our plan for today? Uh, I know, quantum circuit operator, very interesting function. Many of you want to learn more about that, those beautiful diagrams and etc. But when it comes to the algorithm development, when it comes to the circuit design, behind the scene is operators. We really need to have a better understanding of how we can construct our quantum operators. So that's why today we are going to focus more time and do some problem solving with quantum operator. And then once we master these skills, shifting to circuit would be very straightforward. Let us start with the first question. Create a uniform superposition of 8 qubits using quantum state function only.
Oh,
Okay, let's see how Nick would tackle. So he would just start with quantum state. So you see, the immediate things that comes to our mind is that, if this is one of those famous ones, it has a named state, which is uniform superposition, and the second argument it tells you the number of qubits. Okay, and you can see, when we say qubit, meaning that all of them are in two dimension.
okay. Next.
Next, let's see how we can create that using Hadamard operator.
Still support this notation, right?
Yep. So there are two ways. So here we know, those of you who are familiar with, a uniform superposition, you can create it by applying Hadamard. So what is happening here is that we are saying a Hadamard operator act on 8 qubits. And then remember, if you want to apply it on a register state when all the qubits are in the ground state, you can either specify it explicitly, or if you just apply that quantum operator on, let's do it explicitly, register state of 8 qubits, and you're going to get your uniform superposition.
Is it really an 8-qubit one?
Okay, interesting.
This one, did they break it? Hold on. Do it like this. Oh no.
So the only what register state, what's happening there is that you are giving that list is basically tells you what is the dimension of each of those quantum states. We are saying that all of them. So it's very odd to have those particular features, but that's what's happening here. Now the easy way, Nick, we can also show the easy way. So you just don't need to specify your register state. So just quantum operator, and
Yeah,
then
just work like this.
yeah, that's basically, which is almost always this is what's happening in most cases. Like you design your operator or your circuit and then you apply it on a register state. So don't bother with the specifying the register state. Behind the scene, we understand all the dimensionalities and everything, and that piece of code is exactly the same as line 23. So we understand that you want to apply it in a register state, and then the dimensionality of that register state, we get it from your operator. For example, if you, I don't know, let's apply the 9 qubits, automatically we understand that okay, so behind the scene is 9 qubits. and you can easily see that it's 9 qubits. So that's one common thing that you would see, in whenever we want a uniform superposition, just apply Hadamard. One quick comment: this is one design. Another design for applying Hadamard on 9 qubit is to specify that in the order of your operator. So let's also show that just for the sake of explanation. So you can go with Hadamard, and then you can say apply it on, for example, 8 qubits. So this form is exactly the same as the form above that. Okay, those two operators are literally the same thing. So there is no difference between them. Of course, the main reason that we added the above design is that it's easier. But if those of you who like to work directly with the order, that's how you can work with the order. Because if you specify that, in the way that we did it above, the automatic order is 1 through 8, 1 through 9, whatever is the number of qubits. In the order, you have the possibility of applied on whatever qubit you want to apply it. But both of them are the same. Okay, let's move on to the next question. The next question is telling us why, whenever we talk about poly-Z, why, many people, many literature, they call it phase flip. What's happening there? It's literally, as you can see, it's like adding a negative phase whenever you have your one state. For example, applied on state A and B, and look at the formula, it's become negative B. Okay, and that's exactly the same way that when it comes to phase flip error that can be caused by an environment, it's like applying randomly poly Z on one of your qubits. It's just you're flipping the phase of that qubit. Okay, let's move on to the next one. So that's a very generic rotation. So we have an arbitrary unit vector n, which is basically, we can say nx, ny, and nz, and it says how we can create the corresponding generic rotation. So that's a rotation around that unit vector n with a given angle theta. So let's see how we can construct that operator.
Like from built-in constructions or actually manually?
Let's see, let's look at both ways. We can go
Like
with
if I knew nothing about how things work, I would do something like table Pauli metric stuff, or maybe even at least quantum operator. I knew this is my Pauli things. Create 3 Pauli operators. I just create a new one like that. And I would just exponentiate it, I guess, with exactly the same structure.
So that's one approach, that's basically the manual way of constructing that. Okay, that's fine. Now, let's go with the shorthand version. There is an easier way of constructing that. And as you may guess, there is a reason this is called rotation. So we can go with our build, function. So for any rotation, you have to specify the angle. That's the second argument, and then the operators that you want to apply.
Sure, actually, just add them up.
For example, let's all of them, and then in front of each one there is a coupling nx, ny, and nz.
Something like this. I'm lost. Is it the same way? Same thing?
Yeah.
Yeah.
Let's check. Yeah.
Looks like it.
So, which way is easier? Again, it depends. When it comes to circuit design, especially for the circuit, of course, the last option on line 38, that's much easier way of constructing that. So you see, like, the first argument, we are specifying rotation, then the angle. Sometimes that angle, when it comes to the coupling, we call it like, basically the strength of your coupling, and the operator that you apply on. Does it understand that? Yeah, that's even better. So that's, much more straightforward way of doing that. Okay. And by the way, like, because like, these operators, they do not commute. You cannot write down the exponential of summation as multiplication of exponential. Here, we cannot do that. This is one of those examples. Okay, let's move on to the next one. What you see here, like, in some literature, they call it, canonical gate. That's a very common gate. Like, you can easily show that, like, with some, the additional, qubits, this 2-qubit gate, any 2-qubit gates, eventually you can, write it down, in this form. So how we can construct that? First, the first approach that Nick is trying is constructing the operator, the exponent, and then you can wrap it around, like, your you can wrap exponential around that. Okay, so that's one approach that you can do it. Another approach would be like, okay, this is the family of, like, rotation operator. So the only thing that you have to remember is, like, remember by definition, like, there, that angle is pi. So it's like, pi over half, like, that 1/2 is automatically included. So that's the second way of, like, the shorthand way of, specifying that canonical gate. And by the way, like, one other comment, when we say XX, automatically our framework understands that it means Pauli X on the first qubit, Pauli X on second qubit. That's how, like, our framework, interpret that. You see here, like, in this, notation that we have here, we haven't specified any order, because so it's 2-qubit behind the scene, we understand it as, like, look, it is acting on X on the first one, and then uh, X on the second one. So that's literally how we would interpret that. And of course, like, in case we have other examples, just be patient. Like, we are going to show you some other examples. Uh, Next question, like, that's like, another, common, like, you would, I forgot what's the name of, like, that interaction, but, it's very common when we are, studying. Oh, givens. Yeah, givens. Yeah, it's there. Silly me. So again, two approaches. You can create the exponent, directly, or this time, like, let's go with, our rotation operator. So you see, like, again, three arguments. The first argument, you are saying what family of unnamed operators, then the coupling or the angle, and then the type of operators that you want to apply. So that's, like, a very straightforward, like, way of, creating that givens gate, givens operator. Okay, next one, like, you would see the lot, especially for variational approaches, like, the power gates, Pauli power gates. So it's literally like, a Pauli operator raised to power. It says, show it that, it's the same as rotation along the same angle. And let's go with, so for the rotation, there are two ways, like, you can either go with the generic definition of the, now you just wrap it around, simplify. Maybe it gives you,
It depends. Maybe
or we can, like, go with the full simple. Yeah,
similarly.
maybe it's easier if we wrap, if we ask, yeah, that one to be. maybe go with the
So
exponential to trick. Maybe those functions helps us to show explicitly that these two are the same thing.
I'm sure we're doing the same thing.
Yep. Let me double check that. Yes, they are the same thing. Pauli. Let me just implement it on my end. Yep, they're the same thing.
Does this satisfy always? Quite. Maybe you're missing some constant value.
Oh, now good point. It's so that was I totally forgot why I added this example. Now, when you are working with a framework and any other quantum frameworks, you will have Anna, I'll come to your question very soon. You will have this issue that sometimes we say two gates are equivalent, but this equivalency is always up to a phase. Okay, there is always an overall phase showing that these two things are equivalent. So in many literature we do not say that explicitly. We would say that look, Pauli power gate is the same as rotation by a given angle, and then we would tell that okay, so they are the same because the overall phase is not included. Now, if I remember correctly, the overall phase is EI half of pi t. That's what I remember. Let's just try that. Let's see, it gives us the same answer.
What was the phrase?
Exponential e to I half pi t. That's the I pi over 2 and t. I think yeah, if I remember that correctly, yeah, that's the case basically.
Okay.
But in the literature, we don't tell you that. In the literature, what we would tell you is most of the time is saying that look, these two are the same. Why these two are the same? Because overall phase is not observable in quantum. Yeah. Okay. Next, so Nick, there is a question. They run that quantum operator R and N dot XYZ, and they get iteration limit error. Hmm.
Probably because n is undefined.
Yeah. So
And
make sure N, look, Nick define N as a list. So Anna, try that and let's see, you shouldn't get an error anymore. So
but
define your.
this should evaluate to this into that sum.
Yep. You can double check. Yeah.
Otherwise, if you clear it, this is not a valid operator. Basically, what you should have a valid operator here, and it's not evaluates to anything. So it's kind of it should be a failure, not a bunch of messages. Because it depends. It should be better. I'm improving messages every day. Maybe you update the packet. It would be a little bit clear what's happening here.
Hmm.
That this is not a valid operator.
Yeah.
That should be a proper message there.
Anna, he is also answering your question. Okay. Let's see. Another interesting thing that you would see, among all the operators, in the literature, sometimes they call it, fractional phase shift gate, which is basically a phase operator with that 2 pi over 2 to n. So how we can,
This one.
phase shift. Yep. And then n. So remember, whenever there is something common, very likely, we have it, in our 2 pi over, yeah. very likely it is already in our framework. Okay, so either you can construct it, need it phase and then the corresponding angle, or check if it is a named operator that we have in our framework. Now it says if n is one, it's trivial, but just check, let's check it quickly, phase shift one, let's see if it is the same as poly z, and of course you can do the same for 2 and 3. Okay, so that's another common thing, especially for the Nick, just show its quantum Fourier transform circuit, the simplest one. This is where this shift, that's where you would see it a lot. So that green color and with the circle, that's the basically the notation that we use for phase shift.
Controlled phase shift.
That's control phase shift, yeah. Okay, so let's see, next question. Next question is it would have been much better if we discuss about it immediately after that Pauli power, but anyhow that we can also discuss it here. Remember an overall phase in front of a quantum state is not observable. Okay, so that's why if you add a global phase in front of any quantum state, you can easily test that. You can see the I don't know, let's create a quantum state and random pure. Let's call it something state, whatever. Now remember, we have an operator global phase. Let's just apply global phase in front of that with an angle, whatever angle we like. And let's apply it on our state. So that's the whole thing. You see that is not observable. So basically it's
How do you want to test it? By actually
let's see,
measuring?
test it is if it's the same, because it's symbolic. Let's test it if it's the same as state, or we need to give a numerical value.
Well, we don't test in up to a phase, I think, right?
Yeah, it's
Of state of states we do.
yeah.
All right. Yeah.
So you can test it like this, and that's, I know it's a source of confusion, but pay attention in the literature. For example, when you look at the matrix representation of some gates in our framework and compare it with some, I don't know, somewhere another paper, you may notice that there is an overall phase difference. Okay, and it's confusing. You say, okay, there is an overall phase. Why people are not explicit about this overall phase difference? It's only because uh,
Gonna
no operators.
make
Yeah,
sure that we are not testing phase for
yeah,
operators. Just make it our comment.
yeah. It's for the state. Yeah. The reason that people they do that is only because at the level of operators we know that they're different. Exactly what Nick is showing here. When you're comparing the operators, the formula for the operators are the same, but because an overall phase on the top of quantum state is not an observable, many times people they just don't care about them. So pay attention, this global phase, they can cause some headache when you are dealing with some circuits or some specific definition of rotation operator and etc. Especially you may see it a lot when it comes to rotation operator. So for rotation operator, sometimes there is an overall phase difference between the definitions that we have and the definitions that you may see in other textbooks. Okay, so let's see, creates the inverse. So V gate, which is again it's there. Inverse is basically conjugate transpose or dagger of that, how we can create that. So it's literally,
Would this work?
so let's check if it's the same as dagger. We can check that. I never test that. Okay, that's interesting. So why it is like, again, remember, why we are saying, that's interesting, because many times in the literature you would see that, okay, let's apply, inverse Fourier transform, on the top of something. You don't need to basically go through the headache of, doing that step by step. You can just, directly, uh, apply,
But
dagger
for
on the top of that.
operators, it's not implemented. Maybe soon.
Okay. So what else? Those, let's skip through those, the relations. It's, easy. They can check it, let's go. Let's, how much time do we have? Let's look at that circuits. Let's go with the magic ones. We already shown. Yeah. This is also a very healthy practice. Whenever you see a circuit, try to construct it as an operator, a multiplication of bunch of operators, because it helps you to have a better understanding of, how things is happening here. Okay, remember, we should read it from left to right. So the first thing that
I
we
just
have.
wanna just I know. I think this notation I got rid of it. It's confusing. It's a connection of S. It should be
Okay, this is the magic gate, so you can just ask for the magic gate. Let's see, how the magic gate as a circuit, all
oh, it's
without
just
any
oh, it's
parentheses. Yeah,
everything. Yeah,
yeah.
yeah. Actually, it's
I
oh,
know
this-
having that connection there is kind of confusing.
yeah.
So we just say that, no, that connection between two S, we are going to take care of that. But anyhow, let's see what do we have there. So Nick, just focus on operator. Let's not use, quantum circuit operator. Let's just write it down as a composition of, bunch of operators. So first we have S on qubit number 1 and number 2. What you can do is go with the order. That's the most straightforward way of doing that. Or 2S. Both of them are totally correct. Uh, we usually, whenever I do it, I personally go with with order.
Yeah.
So,
So
but
this
again, those two constructs are exactly the same. But remember, when it comes to the operators, the order of action is the same, is inverse of the diagram that you have. So the next operator that we have is Hadamard on the second one. So now we are going to go Hadamard, but this time on the second one. And then we have C naught, but pay attention to the, so the last one is C naught, but the order is 2 is your target, and 2 is your
with control here.
control, and 1 is target. Now, the way, now if we want to compose all of them together, we start the first one that you should write down is C. So it's going to be, again, Nick, go with the operator. I just want them to remember, when, so it's gonna be, you should start with your last operator goes to the left side, C naught.
So like a composition.
Yep.
Or,
Or we can
or you wanna
construct
do this
composition,
notation?
or apply, whatever way, is, uh let's show them the composition,
I
because
think this works.
composition has a very definite meaning in Mathematica.
Okay, I just wanna sure whether it works or not. Okay, but as a composition, we run this one,
And
find
then
this one.
Hadamard on the second one, and the last one. So I
uh,
just want to make sure that, look, make sure that, you have a good understanding of, the order of, those operations is very important. I guess, Nick, uh, on your composition operator on the top line
yeah.
96, you have to put C naught at the very, yeah. Yep. So again, I fully understand. You may feel okay, why people do it like this, and why this circuit is written left to right. But when we apply a composition of functions, it has a, for example, if you look at line 97, it's clear that first you're applying S, then H, then C naught. Okay, but like the order, remember the order, like the sequence of your operator, that's very important. So either you wrap it around one operator or application of one operator on the top of another operator, but pay attention to the sequence when it comes to the circuit design. Okay, so that was one thing that I wanted to make sure that you guys remember that. Okay, let's move on to the next example. The next example is basically like a practice on control gates. This time, let's write our composition with only one single, operator. So let's just have only one quantum operator, and let's inject everything there. So we start with X on the second one. Then here we have control. So we go the family of control first. Say that this is control. Then your operator acting on the Now look. Let me just comment here. Look. You see here, we are specifying control 1 as 1 and 2, and Nick is not giving any argument for Z operator. So automatically, that's how we would understand it. So we would say, okay, whatever is the control, Z will be the next one. So here we automatically understand that Z is acting on the third one. Okay, so it's not given explicitly, but that's what's you don't need to include it, but let's keep it like that. And then we have X on the second one, and then there we have our let's, I know it's Toffoli, but let's write it explicitly, not on the second one and 2. So this is basically the operator composition of that circuit. Okay, so of course uh, exactly the same construct, you can let's wrap it also that one. Instead of operator, let's go with the circuit and adding one extra. You see that's exactly the same thing. For let's that target 3, let's make it 4 just for clarity, when Z, yeah, you see here, that's why we don't, you see, you can change that. So that's why that's an interesting option. So you can act your target can be anything, but again, remember, if we do not specify it, we automatically go to the next one immediately after your control 1 qubits. Okay, let's see. Then that last example, before we move on to the next topic, the circuit that you see here, this is the multiplex gates. You see here, what's happening here is 0, 0, 0, and then Y on that qubit. Then one by one, we are basically including all the combinations. This is basically all the subsets of 0 and 1 with the list of when when all of them are, so not sublist, tuples. Yeah. So this is exactly the same order as you see there.
Oh yeah, that's already correct.
Yeah. Now, how you want, how we can write down the corresponding, operator. So what we need to do, we have to create a series of control gates. So Nick first, he's specifying the operators Y, H, Z. So that's the sequence that we have. And then he's gonna tell us okay, now let's go with operator. Okay, C and order.
The code name.
Yeah, that's better. Name control. That makes sense.
No, because we can't use 0.
Oh, we have, oh yeah, it's this is basically, no, so we have to create 2 lists. So we have to say how we can, split it. Let's see.
Just do this thing and values
Yeah.
of them. I mean,
1, 2, 3. Okay, but remember, 1, 2, 3 is your control. Yep, that's good.
I think it's already fine. I just have to splice it here.
Yep.
It's the other way around.
Mm-hmm.
Right?
So basically, remember, the first one is 0. So in our control C, the first argument is for 1. And these are basically the operators that we have. Oh, you have to remove the reverse, I guess. Yeah.
No. Well, it's the same. So we screwed up. So if this one, because it's maybe we should pad it with the empty one,
Mm-hmm.
and then reverse it. But two. Then reverse. Weird. One, two. It's not quite reverse. What if I just swap this around? Why it's this so hard? Why
Okay,
made
so another trick is like this, Nick, create all the subset of, the 1, 2, 3. Like that's another approach. Subsets of, 1, 2, 3. Okay. And then let's map this one and complement of each case with 1, 2, 3 again. So let's apply a function, open the parentheses, pound, and
well, in
then
this case, I can just pad with an empty one.
pad
If
with an
this is
empty one.
corresponds to a control 1, right?
Yep. No, these are control zeros. Look
Oh,
at
control, yes.
these are control ones. You are right. These are the control ones. Yep. These are the control ones. Now, with the complement is much easier to create that. But with the padding,
I'm just gonna do this then. This is control 1. It's the same thing.
reverse.
Like this
Let's
now is
see.
correct, right?
That's exactly what we want. Yep.
Without any silliness here. Like,
hmm And let's look at our circuit. So that's exactly the same. So you notice, when we have the sequence and all the possibilities, it's kind of a headache. So we had to do it took us some times to basically create what we have here. But literally what we have here, and it is called, multiplex gates. Basically, you have block diagonal gates, and then in a sequence starting from 0, 0, you're applying, all the possibilities, whatever you want. So instead of this construct, you can simply go with the named operator multiplex. So let's go with the multiplex. And then literally that list of y and exactly that. And I don't remember. I guess we should kill the list if I remember that correctly. Yep. So this is exactly, this operator is exactly the one that you see above.
just after compiling it into a single. I'm not sure. Do you
Circuit operator. Ask for the circuit operator.
Okay, right. It's almost the same. Kind of.
Yeah, it's because we have
Outside
yes.
dimensionality thing. I have
So
to. We have to
then
specify dimensions, right?
dimension 2, 2, 2. So we have to go with the quantum basis. Oh, let's go order 1 through 4. 1, 2, 3, and 4.
That's smart. I don't remember how multiplexer works exactly.
Let me just double check that. We have it in our documentation, but I guess you guys got the message. It's some of the named operators. Where is the multiplex? Let me
No,
just
no,
find it.
it's not even returning anything, so it was kind of a bad idea.
Rapid maybe. Hold on a second. No, that's so. Just change the basis. No, the order is not good. Just give the basis 2 and 4 instead of order. Yep. I guess you crash your kernel.
Yeah, I already reloading it. So
So basically, a multiplexer is a block diagonal, and the top one, what you see here, the first one, it says Y. So Y, it means what's happening there is the first 2 by 2 is Pauli Y, and then move along the diagonal elements. Then the next one is Hadamard operator. Then the next one is Z operator, X, and so forth. So that's how we would basically construct our multiplexer operator. And it makes your life much easier when you have fancy control gates like this.
still a bit out of order. It's not. Oh, and 1, 2, 3, 4 with the basis. What we've tried.
And these two should be, maybe we need to do some simplification on the circuit because it's 16 by 16. So let's look at just the matrix, and we can compare the matrices.
It's not. Well, I can see by the picture it's kind of in reverse for some reason.
Let's see. I have now. Let me just look at our documentation.
Yes.
Just I do not remember that Nick, for multiplexer, we do not have. Do we need to add quantum operators wrapping around those named operators, or we don't need to do that?
But we may give it. Oh, maybe what we should do, because
Oh, it goes on the first one.
we should do something like this for everyone.
No, hold on, we are just specifying the block diagonal. I don't think we need that. So what we need is let's see.
Well,
I think we need to wrap each one of them around quantum operators. I do not think it's just wrap around X, Y, Z, all of them around quantum operator, and we can kill the order and the basis. And I think it should work. No, it's still C. That's the same as before. That's interesting.
let's just wait. We don't have to focus on it right now.
Hmm.
Multiplexer is very.
But the idea of multiplexer is literally a block diagonal matrix. So it's I thought I remember all of its construct, but it seems I have forgotten how we constructed that. Just a sec, let me check one thing on my end. Okay, we can, let's show a simpler example. Let's have, for example, quantum multiplexer. Let's have an operator, quantum multiplexer. Let's kill all of that. Simpler example. For example, let's go with uh, uh, x, y. Yep. So now this should be x, not x, y. Let's go with identity and I. Identity and I. Actually, identity and I, and it should be the same as control C. So that's exactly what we are saying. So it should be the same as control C and Y. And this time, was one. So empty list and then one. Or maybe one and empty
So I think
list.
the other way.
Yeah, that way. Yes. Okay, so that's literally like, and then if we switch them, it's gonna be the opposite. So that would be empty. Yep. Now I guess now you guys have a better understanding of what we were discussing regarding the multiplexer. So multiplexer is the most advanced way of creating, like, Robert, yes, we are gonna upload this with the solutions. The most advanced way of creating the control operators. So but it's kind of counterintuitive, but it's very nifty. It makes your life very easy. Okay, let's move on. Very quickly. Let's comment on quantum measurement operators. I don't think we are gonna have time to discuss circuits, so we can discuss circuits next time in more detail. But remember, we already gave you a good taste of circuit on day one. Remember, as we said at the very beginning of this session, quantum measurement is very different from everything else that we have in quantum. A big headache, lots of discussions about them. But anyhow, for computational purposes, either you can go with usual projective measurements, okay, like here. What we are doing here is we are measuring qubit number 1 and number 3 in computational basis, okay, and then random pure state, random pure state of 3 qubits. So the measurement, what we do here is literally just measuring 2 of the subsystems. And one other comment, remember, whenever we are not specifying the basis, it is the computational basis, which is, I think, most of the time you guys are working in the computational basis, unless you want to do the fancy things. The result of quantum measurement operator on any state is a new object, which is quantum measurement, and there are tons of interesting features that you can extract out of that quantum measurement. For example, the corresponding probability plot, the probabilities as an association, and then you can also ask for the corresponding states, these are what you may call them post measurement results. Okay, after the measurement, what is the corresponding state, and what's happening there. Remember, your original state was the state of 3 qubits, okay, and we were measuring only 2 of them. Now the next example, you see here 3, and we are measuring only 2 of them, one and number 1 and number 3. Now let's measure all of them. So we can, another approach is just measuring all of them. And of course, this time when we look at the probability plots, we are gonna get at least this is 8 different results that corresponds to your measurement. But anyhow, one interesting feature about measurement is that in our framework, you can do a sequence of measurements. You can have a composition of measurements, or you can have an operator, literally that one. You can do it in 3 steps. You can say that look, first measure number 1, then measure number 2, then measure number 3. This is one another way of constructing your measurements. Remember, these are different quantum states. Sorry, these are different quantum systems. So the sequence of measurement, how you construct that, is not important. Let's call it the same state. Yeah, just showing that it's exactly the same probability. Okay. One other thing that you can do in our framework is a generic measurement. We usually call it POVMs. So what's the idea here? In the usual projective measurement, the number of results that you would get is the same as the dimension that you are working with. Okay, for example, if you are measuring spin, it's just two potential answers. Or when you have like 8 qubits, 8 outcomes. Okay, that's exactly like what's happening here. What you can do, let's look for these are the potential outcomes, 8 outcomes. With POVM, you go beyond the projective measurements. So it means, first of all, after the measurements, the states, they have overlap. Okay, they are not orthogonal anymore. Okay, this is one case that happens a lot when those of you are familiar with the weak measurements. That's exactly the case. Like your measurement results, they are not orthogonal anymore. Why POVMs are interesting? Because remember, when we do projective measurements in quantum, we always remind our students, projective measurements, then you cannot simultaneously measure, for example, two operators that are non-commuting, like Pauli X and Pauli Y. You cannot measure them simultaneously. But if you release this condition of projective measurements, yes, you can measure them simultaneously. And that's exactly what's happening in the weak measurements. For example, with weak measurements, you can simultaneously measure Pauli X, Pauli Y, and Pauli Z. Okay, but the result is that these states are uh, overlapping. They are not orthogonal anymore. I hope you guys remember the states that you see here. This was one of the problems that we did, last time during the last sessions. And I told you, like, the trine states. And I told you, look, these are very interesting for POVMs. So what we are doing here, we have a bunch of states. Remember, it's a two-dimensional system, but we have three states. And these states, they are not orthogonal. There is an overlap between them. You can easily see that, like, there is an overlap between them. What we can create the corresponding operators for each state. Let's you can see, conventionally in quantum we would call them the corresponding, like, projectors. Then POVM is basically the list of those elements. Conventionally, like, remember, like, this is those operators. All of them are, positive semi-definite matrices. Their summation is also identity. These are the usual things that we have because, like, they should be physical, and also the concept of probability. We can easily check all of them. Nothing fancy here. But anyhow, long story short, you can have generic measurements. So this time, like, you are gonna get, like, a different. So this is, look at here. What is interesting, like, just look at the, like, you see here in the summary box, is not a square matrix anymore. Okay, it's a rectangular matrix. So that's one thing, like, that kind of fingerprint of, like, POVM. And although you are measuring, like, a two-dimensional system, you get three results, and each result corresponds to those states that we define at the very beginning. We can look at probability plot, or, like, E1 corresponds to state number one, E2, and E3. So it's like I'm measuring, it's like measuring a spin, one half a spin system, but because I'm doing a generic measurement, we are getting three results. Okay, so I feel like we gave you enough, basically all the functionalities that you need. And now next time, tomorrow, we are gonna focus more on circuit. But literally, like, whenever we discuss the circuits, behind the scene is quantum operator, quantum measurement, quantum state, and that's how we are basically dealing with them. So and whenever it comes to algorithm design, that's a very good strategy. Always think in terms of, like, your operators and what's happening to the state, rather than just focusing on circuit by itself. So tomorrow we are going to focus more on the circuit, and we are going to review everything, because circuit has all of these concepts together: measurement, operator, state, all of them together. And hopefully, like, you have a better understanding of, like, our quantum framework. By the way, all of the notebooks that we have shown you here, they are already on that series material. You can download them from there. I think we just need to include the answers. So, like, we will also include the answers, so you will see the notebooks together with the answers. Any question? Any Nick, is there? We have about less than a few minutes. Would you like any comment you would like to add?
I guess. Well, I would love to discuss more in detail, but I don't think we have time. So.
So maybe we can do it next time. Like it's um. By the way, like quantum measurement, like maybe just show like the input form behind the scene. What is the quantum measurement? Maybe that's interesting for our
Quantum measurement
users.
itself.
Yep, as an object. Yeah. So you see, like the behind the scene, like
It's easier to show it like instead somehow this one. Inside of quantum measurement is underneath it is just a measurement operator itself.
so like you may say, okay, so while you are showing me like the quantum measurement, most of like these issues are for communication purposes. Like if we show you, if we tell you that look, behind the scene is the same as like what's happening to that operator, it would say then while you are showing me like the application will be very complicated. And then when it comes to like the actual measurement results, the way that we do it originally, like if you guys like if I don't know if anyone attended our very first study group. If you may remember, in the very first study group, we told you that quantum measurement is for us behind the scene is like a categorical distribution. uh we kind of like get rid of that design because um there are much better way of like dealing with quantum measurement. For us right now is like the way that you can see it is like this: whenever there is a measurement, it's like you are including detector, a sort of, let's call it, classical system. Some people, they would call it environment. The way that we deal with that is that we go to a higher dimension. Okay, it's like in that higher dimension, in a like much larger Hilbert space, we basically include everything. And that's why when you look at the diagram for your measurement, it's the same diagram as a quantum state.
A little bit ugly because of a label, but
Yeah, just change the label. So behind the scene, like what we do is that, okay, so you want to do whatever you need to do. So it's like entangling, coupling your system with a detector. So behind the scene, we do all the couplings. And if you ask why we do that, then any future operation on your measurement, you can easily do it in a higher dimensional Hilbert space. But you don't need to worry about that. Like, this is the thing that like, we kind of, we save that information, and behind the scene, we have that. That's why like, on the top of a quantum measurement, you can apply an operator. So that's one of the neat features of like, our framework. Like you can have a sequence of measurements, you can have operator applied on the top of like a measurement results, and you can do all of them together. Now we have to remember like what's the dimension now. Is it 3 6? What was the dimensions? One two
it's like
three
3-2 because it's a
three
pure
two.
VM.
Yeah,
It's very tricky. Like I can apply something like this.
yeah.
That would be. Mm, oh, what? Just happened here?
Let's just apply that this one on it should work on the first one. Yeah, the first one was the 3 dimension. I don't remember
You
which one
should have
was which.
done it like this. This 2-3.
Just switch the two.
No, it's fine because order
Oh,
is
the dimension is one. Oh, yeah, 2 3.
for some reason unordered. I think it's still okay. We apply this guy. Oh my god, undefined state rather.
Yeah. So basically, like, you can apply directly on your states and, like, keep evolving them. But anyhow, remember, like, we do it in Bianca, like, the question is, like, what's the benefit of going to the higher dimension? Like, it's like you're saving all the information about your quantum system. For example, like, conventionally, when people are talking about measurement, for example, they will tell you that, spin, measure it, and then your result is, like, your result is a mixed state, right? Like, you get a, for example, a mixed state after the measurement. So it means if you want to do, like, further operation on, like, saying that, if I get positive, what's gonna happen? I just want to apply, like, an operator if I get positive. Conventionally, if you do not save that, you cannot do it. Okay, you have to construct it manually. But what we do is that going to higher dimension is like using an ancillary, like, quantum system, and we save that information. It's literally like, I don't know, if you guys are familiar with the idea of, for example, quantum channels. One way of describing quantum channel is saying that, okay, you have your state with this environment, this happens, no environment, for example, it stays as it is. So it's literally exactly the same approach. Like, you go to a higher dimension and you can preserve everything there, because in that higher dimension, all of your operation would be unitary, linearity, and everything. You are not going to lose any information. But you don't, again, like, it was just an explanation, like, what we are doing behind the scene. Okay, like, it's not like you don't need to care about, you don't need to understand, like, how we are dealing with it. But that's a very nifty construct that we have, so you can do lots of other things on the top of your measurement results. Like, what's happening here, you see here, like, Nick is applying a poly operator on the first qubit, and then he does another quantum measurement on the top of the first qubit. So we can do it only because, like, behind the scene, like, we are going to those higher dimensions without showing it to you, so you don't see it immediately. But I guess, like, if we ask for the state of the quantum measurement, they can see for the state, right? If I remember that correctly. Oh yeah, it's even visible here. What, you see here, you can see it here, like,
This is the eigenvalue, so this measurement operator. It's like first we measured with POVM and got three results, those E1, E2, E3. When we applied a new operator, or necessarily don't apply it, just measure it again. But
mhm,
normally we kind of double our measurements. On the same qubit, we measured twice with two measurement operators.
mhm.
We doubled our probability distribution.
Again, Bianca, related to that question, look at exactly what's happening here. If you use a mixed state, you cannot see the sequence of measurement results. You cannot see, okay, I got E1 for the first one, which was a POVM, and then for the second measurement, I did a projective measurement. If you go with the mixed state, like, basically, if you don't save that, you are losing that information. You don't see that information. It's kind of like, just to give you a taste, it's kind of like, similar to what's the idea, like, it's kind of similar to the idea of purifying your kind of. Okay, when you purify your system, you go to a higher dimension and you're saving everything in a pure state, because dealing with that pure state is easier because you're saving, more information. It's kind of similar to that, not 100% exactly the same. Okay, I guess, we are running out of time, so uh we'll upload the solutions. Any question on community or directly quantum at wolfram.com, let us know. Any issue, if you were not able to code anything, please let us know. And in case if you notice any, for example, like, maybe, for example, today when I was looking at documentation, I realized there's a typo somewhere, so users were not able to reproduce our results. So maybe there is an issue somewhere or a bug. If you notice anything, let us know. We would take care of that, immediately.